We already discussed how the shortest curves in the subRiemannian Heisenberg group are linked with a variant of the isoperimetric problem on the plane. The solution to this problem are arcs of circles and pieces of lines. So to obtain the subRiemannian geodesics, we just need to lift such curves. So we are now ready to write the formulas for the geodesics in the Heisenberg group. Okay, so let's consider the plane. Let's consider circle. Maybe let's first begin with the circle like this. So a circle of length, let's take a 2 pi over k, so k is going to be a real okay, k different than 0, passing through 0.00 at time 0 is, so let's call it x naught y naught t. Okay, so it's the usual circle, cosine of t, sine of t, but we have to rescale the time, and we have to translate the x variable by 1.1. So it's going to be cosine kt minus 1 divided by k, sine of kt divided by k. Okay, this is for t in the interval 0, 2 pi over norm of k. So, so the center of the circle is here, and in the negative x-axis. Now, if x is positive, then we are parametrizing this way, if k is positive. So if k is negative, we're going the other direction. If k is negative, okay? So in k positive, we are going to enclose positive area. K negative, we are going to enclose negative area. And actually, this can also be understood in the limit case when k is equal to 0. When k is equal to 0, this degenerate to the straight line. So let's write it for k equal to 0. The circles degenerate to the line 0. No, degenerate to this line here. 0t. And is defined for all t in R. So this goes to infinity. Okay, very good. So these are solutions of the isoperimetric problem. Now let's take any other circle. So to obtain every other circle, we can rotate. We rotate by an angle theta in R mod 2 pi. See, so the rotated circle by theta of x0t, y0t, this is, so the rotations by definition is the matrix cos theta minus sen theta cos theta. Okay, so we rotate, and then we have the circle we had defined before, cos kt minus 1 divided by k, sin kt divided by k. Okay, we perform this matrix product, cos theta cos kt minus 1 over k minus sin theta sin kt divided by k, and then we have sin theta cos kt minus 1 divided by k plus cos theta sin kt divided by k. Right, so these are 2 by 2 vector. Okay, so these are the circle on the plane. Pieces of these circles will be lifted to get the geodesics. Okay, so we can calculate zt as the, let's make capital T, zt as the lift of r theta x0t y0t up to time t. The formula tells us namely, so zt was the integral from 0 to t of 1/2 xt y dot t minus x dot, let's put it y first, yt x dot t in dt. Okay. Now we have to perform these derivatives. We have to calculate the derivative of these vectors in t and then integrate. Okay, so let's do a little bit of derivations. So I copy here the formula for the curve. Put it here for a moment. Then let me calculate the derivatives. The derivatives is going to be cos theta minus sin kt. Now this k will cancel with this k. Minus sin theta cos kt. The one below instead is minus sin theta sin kt plus cos theta cos kt. So this is the vector x dot y dot. Okay, now let's put it up here. This is the interval between 0 and t of 1/2 of, okay, cos theta cos kt minus 1 divided by k minus sin theta sin kt divided by k multiplies, here to parentheses, multiplies y dot, so it's going to be minus sin theta sin kt plus cos theta cos kt. Then minus, let's not forget about this minus. Let's try that. I will remember to change the signs here, and I put already plus. So y is sine theta cos kt minus 1 divided by k plus cos theta sin kt divided by k. The multiplies, now I have to change the sign of y dot, so it's going to be cos theta sin kt plus sin theta cos times cos kt integrated in dt. Okay. Now it's better to have a bigger piece of paper. Okay. Yeah. Let's see that I will copy from my notes. Otherwise, I will not be able to do this calculation. Okay. Let's multiply. So this is so zt is equal to 1 to k. So I put in evidence to k, 1 t minus cos theta cos kt minus 1 sin theta sin kt plus cos theta square cos kt minus 1 cos kt plus sin theta square sin kt square minus sin theta sin kt cos theta cos kt plus sin theta cos kt minus 1 cos theta sin kt plus sin theta square cos kt minus 1. I forgot to write, so cos kt plus, almost done, cos theta square sin kt square plus cos theta sin kt sin theta cos kt dt. So what I did, I just multiply everything one by one. And okay, say if I have the correct number of terms, so 2 times 2, 2 times 2. So 1, 2, 3, 4, 5, 6, 7, and 8. Okay, these are the correct number of terms. Okay, so now of course what we are going to use is the fact that cos square plus sine square is equal to 1, and we are going to have a little bit of cancellation, right? So this together sum, and likewise this sums with this. So this will, okay, so maybe that's why. So this will be joined with this other one, with this other one. Then what else? This one and this one will actually delete each other. Likewise, this one and this one. So at the end, what we will have is 1 over 2k, the integral between 0 and capital T of cos kt minus 1 times cos kt, which was this term, and then we put this term here. So plus sine kt square. in dt. Okay, how can we simplify this as well? I will multiply this times this, get a cosine square, which sums with this and gives me 1. So this is 1 over 2k integral between 0 and t of 1 minus cos kt in dt. Okay, now you can integrate. So the first one is going to give you t, so it's t over 2k correct. Yes, correct. And then integral of cosine is sine, evaluated, but I have kt, so I have to change length. So it's going to be minus sine kt over k, and that also this, don't have to forget, 2k square. Okay, which maybe it's better to write it as I wrote in the notes, to be tk minus sine kt divided 2k square. Okay, so let's conclude what we have proved. We proved that the length minimizing curves starting from the origin in R3 are the smooth curves gamma x, or let's call it gamma 1, gamma 2, gamma 2. Okay, no, x, y, z of the form x is equal, so x of t is equal cos theta cos kt minus 1 by k. So these are the the planar curve, the planar component. Sine theta sine kt divided by k. Y of t is sine theta cos kt minus 1 divided by k plus cos theta sin kt divided by k. And the third component is equal to kt minus sine kt divided by 2k squared. And this is for some parameter theta, which is an angle r mod 2 pi z, and another parameter we'll think as the curvature of the of the circle. Okay, so such curves are defined for t in the interval 0 to pi k, norm of k, right? Up to this point they are minimizing and have length. So what's the length? The length was a circle of radius 1 over k. So the length is 2 pi over k. Okay. Now, if you go also see at this what's happening when k is equal to 0, all these formulas converge to something, so we can really still make sense. And as we said, this converges to a line, and I will write what the limit of this. So when k is equal to 0, these curves give as limit, or degenerate case, the lines, let's write the lines, x t is equal minus t sine theta, y t is equal t cos theta, and gamma 3 z. Actually, we don't really need to look at what is the limit of this area, right? So actually, let's check it, because we know lines don't span any area, right? And then you see that this is so the first expansion is in the Taylor series is kt, it gets removed, and then is third term, is of third order. So when divided by 2k, when k goes to infinity, this goes to when k goes to 0, this goes to 0. So the area is 0, as in fact the line does not span any area. Okay, so we found all the length minimizing curves in the subRiemannian Heisenberg group starting from the origin. To get all curves, one just needs to apply left translation to these curves. Okay. Now let's draw some consequences of this characterization of geodesics. So let's draw some consequences. So let's try to understand what we have proved. So we have proved that so we have this planar projection, which is going to be a piece of a circle, and then there is the lift of the curve. So when you follow the curve, you see the area is going to be increasing, and it's increasing not really linearly. It's increasing with this. So this is an increasing function, but it's not linear. Okay, so we are going to have some spiral property here like this. I will later also show you some picture draw with Mathematica. So it's like something like this. Okay, good. So this is what we have proved. Now, so what we understand is that, first of all, if you have a point that is on the z-axis, so if the point x, y, z in R3 is on the z-axis, in other words, x equal y equals 0. So if you have a point like this, then you see that you have infinitely many geodesics, right? You take any circle enclosing area z. So let's say, okay, let's say z is non-zero and z is non-zero. Then every circle with area z leads to a geodesic arriving to this point. Right? So the geodesics are not unique. So then every circle enclosing or with area z leaves as a geodesic to arriving to x, y, z. And we have one parameter family of this. We have one parameter family of such circles. Right? So it's interesting because these points are arbitrarily near the origin, right? So it means that there is no neighborhood of the origin where you have uniqueness of geodesics. So first, this implies that therefore this geometry is not Riemannian. Okay. However, it is true that if you take a point not in the z-axis, then the length minimizing curve is unique. So if xy is not the 0, 0 point, then there exists a unique length minimizing curve. And also from 0, 0, 0 to x, y, z. And again, what you have to do, you take the point x, y, and you observe that there exists a unique arc. There exists a unique circle with such that this area here is z. And you see this by continuity. Okay, now, what else? Okay, the last comment about this non-uniqueness. So if 2 points are in the z-axis, distinct points, then they're joined with infinitely many geodesics. Now, let's apply left translations. So the z-axis is the integral curve of the vector z. So I make you observe that the z-axis is an integral curve of the vector dz, the one we call it capital Z, which is left invariant, is preserved by the product structure. And consequently, if I apply a left translation, then the z-axis will go to any other Euclidean vertical lines. So therefore, left translations send vertical lines to vertical lines. And with vertical here, I mean really Euclidean translations of the z-axis. Of z-axis. Okay, so the consequence is that now, if you take 2 points that are in the same vertical line, then they don't have a unique geodesic between them. So if P, Q are in R3, and they are such that they are in the same vertical line, such that P1, P2 is equal to Q1, Q2, and say that they're distinct, so P3 is different than Q3, then there exist infinitely many geodesics between them. Okay. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel. clicking below. Bye.